Okay, hello everybody. So we're going to have a sort of session with a sort of hydrodynamic theme this morning to start with. So I'd like to present the first speaker. It's Herbert Spon, who always seems to be in India while I'm in India. So it's always a pleasure to meet Herbert here. So he's going to talk to us about hydrodynamic scales of integrable many particle systems. So I'll hand it over to you, Herbert.
Thank you very much for this kind introduction and for the possibility to speak here. I mean, so my pleasure. And so the title is a complete overstatement, of course. You know, it's overambitious, but it gives me sort of the chance to explain you a little bit, you know, what the whole talk is going to be about. I mean, so this is, I mean, integrable many particle system, of course, has a very long tradition. The first point is that what do I mean by integrability? Okay. Now, in terms of hydrodynamics, what I mean by integrability is that beyond, you know, the standard conservation laws, which sort of every mechanical system would have, like density or number and momentum and energy, you will have many more conservation laws. In fact, you have extensive number of conservation laws. So if n is some sort of, you know, size of your system, and then you will have n conservation laws. And so, of course, you know, the system is sort of constrained, but you know, phase space is typically 2n. I mean, so there's still, you know, a lot of room to move around. And so this is sort of what I want to do now. The hydrodynamic means that we are looking at states which are actually random initial data. I mean, so otherwise, I mean, it would be difficult to think about the hydrodynamic scale. And so we are not looking at ground states, you know, which have been, of course, studied also, and it's a totally different area. But here I'm concentrating on initial states where you're sort of, you know, highly excited. I mean, you're way above the ground state energy. All right, and now, I mean, this is actually a sort of an area where I mean, there has been a lot of activities. I mean, there are two very important and fundamental papers in this area. I will not mention too much of the literature because, you know, it would be endless. But it's sort of 8 years back where people sort of first discover how to even write down the correct hydrodynamic equations. And I hope maybe that during the talk, I mean, you get some vague flavor why this was such an important step. But since then, I mean, there are sort of huge activities, and of course, you know, there's a wide variety of integrable many particle systems, and therefore, you know, the experiments. I mean, anyway, so many of these things I cannot explain here. And the idea of the talk is that I want to concentrate essentially on one single model, which is what I call this Calogero fluid, which sort of has sort of, you know, the level of being sort of a particular model you can focus on. I mean, it has also difficulties which are sort of characteristic for other models. Okay, so the other prelude is that since we're talking about integrable systems, I mean, these are very exceptional and rare animals. It's very fine-tuned. I mean, you know, if I modify the interaction just sort of a little bit, then you will see something totally different. And so, of course, you know, there's another area which actually at the ICS, I mean, people work on this, you know, what happens if the system is sort of nearly integrable. I mean, you start from an integrable system, then you perturb, and then it's nearly integrable. Again, I'm not really talking about this. I just would like to explain you know, what is sort of happening on this hydrodynamic scale. Now, most of the work which has been done in this area is actually related to quantum many-body. I mean, that, you know, all the sort of drive sort of actually came from understanding particular quantum many-body problems. And I, at some point, thought that, you know, I mean, if this is something which works for quantum many-body, I mean, it also has to work for classical many-particle systems. And so the talk will be actually, I will not touch a quantum mechanical model at all, and the Calogero fluid will be just a standard system from classical mechanics. Now, since it's integrable, we are automatically constrained to one dimension. I mean, one spatial dimension. I mean, there are sort of some attempts to go to higher dimensions, but, you know, then it becomes sort of rather nebulous, and there are not very many results. So the system will be in one dimension. Okay, so let me first flash to you some of these integrable models. I mean, here I sort of made a list, I mean, of some representative. Of course, it's far from being complete. But the way you should think about this list is that, you know, each model has sort of its own very special characteristics. So, you know, so the Lieb-Liniger delta Bose gas is just quantum particles with the delta type interactions. You have the spin chains. I mean, you have the total, that is the colloidal fluid. I will sort of explain in great details. But you have other systems which presumably in this audience nobody ever heard about. I mean, there's something which is called the ball-box system, which is sort of a discretized nonlinear wave equation where, you know, you make both discrete, I mean, space discrete and also the values at each point discrete. And then you have a particular sort of discrete update of the dynamics, and then you look at it and you realize that if you do it sort of in the right way, I mean, you also get an integrable system. I put here, I mean, you know, since particle is sort of, you know, a little bit vague as a notion, I mean, you know, it also includes nonlinear wave equations. I mean, so the quadratic Friis equation would be included. I mean, there's a nonlinear Schrödinger, et cetera, right? I mean, so it's a long list, and the plus, plus, plus means that, you know, I could list more. But what I want to emphasize is that, you know, each one of these models look a priori very different, right? I mean, if I write down the quadratic Friis equation, if I write down the Lieb-Liniger, I mean, there's just no overlap whatsoever. And you have very specific methods in order to study each one of these systems. I mean, if I know something about quadratic Friis, I mean, I cannot immediately translate to the box ball. I mean, these are sort of very different animals, so to speak. However, and that's, you know, when I started working on this topic, I mean, it was a real surprise, and I still find it sort of surprising. Once you go to the level of the hydrodynamic scale, all these sort of, you know, distinct properties are in some sense lost. I mean, on the hydrodynamic scale, you always have the same structure. And you know, when I talk about always the same structure, it's sort of like for ordinary fluids. I mean, you know, I can take ordinary fluids, and you have different interaction potentials. Then, of course, you know, when you go to the Euler-Navier-Stokes equation, then, of course, your hydrodynamic functions are different. But the structure of the hydrodynamic equations, of course, is independent of what kind of particular interaction potential I choose, as long as it's short range and has certain general properties. Okay? Okay, so now you see in this, if you think about ordinary hydrodynamics, there are sort of two elements to ordinary hydrodynamics. First of all, you have to understand the equilibrium state. You know, that's in some cases simple, but in other cases it might be more complicated. You have your phase transition, so then this might become already sort of a problem which you know, requires quite some attention. But once you understood the static features, what you know, the ordinary Gibbs ensembles, which sort of would describe statistical mechanics of ordinary fluid, has to be replaced by something else which is called generalized Gibbs ensembles, and which simply reflects the fact that we have so many conserved quantities. Okay, so there's a really static problem. You want to understand essentially sort of, you know, what is the generalized thermodynamics of such a mechanical system. And then once you understand this, then of course, you know, there's sort of the second step, namely going from the picture to from the static picture to a dynamical picture. And there, it's, you know, what you teach your students about hydrodynamics. I mean, you assume that if I look at the little fluid cell, I mean, you know, you see some state which is sort of stationary under your dynamics. For ordinary system, you know, would be just sort of a standard Gibbs measure, or Gibbs state, which sort of is characterized by the 5 conserved quantities. And then you assume that, you know, you have little fluid cells, and then in each other fluid cell, you know, the parameters are varying. And then, you know, since these parameters are slowly varying, you know, in each cell you can sort of define rather precisely what you mean by temperature, by density and energy, and then these quantities are then governed by hyperbolic conservation laws, and that gives you the hydrodynamics. Okay, so now of course as I said, I mean, this is sort of not what you know. I just want to explain this in the context of the colloidal fluid. I mean, what I want to emphasize is at this point, you see. When you derive ordinary hydrodynamics, even if you know the statics, if you want to write down your hydrodynamic equations, you have to know what is this thermally averaged currents. You know, this is when you want to write down the Euler equations, you need the pressure, right? And once you have the pressure, then you know somehow, you know, you can understand of how to put the pressure into your equations of motion. And the big advance, which is sort of from 2017, 16 is that people understood how to write down this GGE average currents. So I'm not going to enter into this, but this was a very, very important and big step, because unless you know what the correct currents are, of course your hydrodynamic pictures becomes completely empty. I mean, if you want to write down the local conservation laws, you better know what the currents are. And before, this was something which maybe people didn't think about so carefully, but it was a big step. Once you understand it, then of course somehow sort of in retrospect it looks rather natural, but that was very important. Anyway, so let me go a little bit into the specific model which I want to study. No, I have one other preload. Okay. Yeah, so this is maybe another thing which I wanted to explain before coming to the concrete model. You see there is, so I'm going to talk about Euler hydrodynamics. I mean, so it's just ballistic scale. I mean, there is something like also, dissipative correction, but that's a different talk. Okay. So now there's something which is studied a lot. I mean, this is sort of what people call soliton gases. That's also big experiments. I mean, you have water tanks where you can see these things. And so the typical model which you would do is sort of like the Korteweg-Friis equation, which is a nonlinear wave equation. And for the nonlinear wave equation, people understood already that there are, sort of particular solutions which are called solitons, which sort of, they're traveling with just sort of translating, I mean, it's a shape which is sort of moving linearly in time. But then you can have soliton-soliton collisions. And there, the amazing thing happens that if you have two incoming solitons, I mean, they're well defined, and then there's some intermediate time where there's a lot of mixing, and when you look at the solution of your wave equation, you cannot say which soliton is which. But if you wait long and long, and they separate, and the surprising thing is that, they sort of come out of this collision exactly with the original shape, except for a certain scattering shift. Now, this is something, now once you have two, you can think of 10, and then you can think of n, and then you can think of soliton gases. And that's another area in this corner which is sort of, which I'm not going to talk about. It's a famous paper by Chenadi L, who sort of discovered how to write down sort of, the hydrodynamics based on solitons. Okay, so the elementary objects are solitons, and then they interact, and then on a large scale you have something which is called soliton gas. And now, what I want to emphasize is that in the models which I listed, and of course also for the Karlotschauer model, the elementary objects are actually the particles. You see, the particles behave as if solitons in the nonlinear in the nonlinear wave equation. And that's something which took me a while to understand, and so let me just sort of dwell on this a little bit. I mean, what is happening. I mean, so here I put sort of like the scattering of three particles. So here time sort of goes to minus infinity, and the three wave packets, if you want to, for this nonlinear wave equation, are coming sort of from infinity, right? And then of course there's some mixed region which you cannot distinguish who is who. But then as you wait long enough, I mean, you have again sort of three solitons coming out. And it's like in the Newton's cradle. I mean, so all what happens is that the incoming velocities are actually are just sort of inverted in their order. I mean, this particle which was to the left at the beginning, at the final time is all the way to the right. And of course, you see, if it would be a non-integrable system, it would look totally different. I mean, it would be also almost like a random map. I mean, it will have no fine structure, but that's sort of the hallmark of integrability. That the scattering process, which of course you might wonder how is the scattering process sort of connected to hydrodynamics. I mean that's a big topic, but I mean on that level on that level of description, you see all what happens is that of course this trajectory sort of shifted slightly. I mean so in this one, but now the shift actually can be computed on the basis of the two particle scattering shift, right? And so now the question is, how do you compute this two-particle scattering shift? And when you look at the TODA and when you look at the delta Bose gas, you see that the way how you compute the two-particle scattering shift is just literally what you tell your students. I mean, you take two particles, either quantum or classical, and you let them scatter, and then you see what comes out, right? And so this is why I want to emphasize that the model which I'm sort of have in mind at the moment, they're all particle-based. the objects, the elementary objects are really the particles. But when you look at the scattering, they behave just exactly like the solution of this nonlinear wave equation. And so I want to distinguish here two cases, and that some of these generalized hydrodynamics is based that the elementary objects are solitons, which themselves have some internal structure. This is soliton based. And the other ones are sort of particles. Now, of course, also quantum particles have, in some sense, they have wave functions, so they have also some sort of intrinsic structure. But in any case, it's sort of in the usual parlance. It's certainly a particle. And the amusing thing is that in some cases, you can have both. If I look at if I look at the total lattice, it will have a soliton gas picture, and so this is then soliton based. It has also a particle picture, and then it's particle based. And of course, for each one of them, you have a hydrodynamic scale. The hydrodynamic equations will be actually different because the scattering between total particles is different than, it's distinctly different between two particles and two solitons. And so your equation sort of, will be not identical, but the structure of the equation will be the same. Okay, so I guess that far for the introduction, and which took already almost all of my time. But anyway, so this is still think maybe it's useful. Okay, so now let me sort of be much more concrete, and let me sort of tell you a little bit about this Calogero fluid. So this is a classical fluid. So it's in one dimension, and the interaction potential, which I've written here, is the 1 over sinh squared. So it goes like 1 over x at small distances, decays exponentially. And since it's repulsive, if particles, if I order them initially, the order will stay the same, right? And so you can think of many particles. Let me think of them first, sort of, on the full real line, and so I order the particles like this. Okay. Now there are two sort of limiting cases which are in some way a bit easier to understand. There's the high density, where you just sort of look at this. Sort of short distances, so you just replace the potential by 1 over x squared. This is called the rational or Calogero model Sutherland model, and this actually on the hydrodynamic scale is not so interesting, because despite the fact that it's strongly interacting on the hydrodynamic scale, it really looks like an ideal fluid. Anyway, so now we have also the low density. That's where you think particle far apart, then you can basically replace the pair potential by the exponential. But then if I look at my neighbor, I keep the exponential. But then if I look at the next neighbor, then it's exponentially down compared to what I had already. And so in this list, rather than summing over all, I just I have fixed my labeling. I just sort of sum over neighboring labels. Now you see, once you do this, I have removed the 1 over x squared repulsion, and so for the total lattice, actually particles can cross, right? That's sort of not preserved in the system. Okay, so that's fine. So you have two limiting cases, but now I want to really look at the Calogero. Okay, and now what I said in the beginning, you need many conservation laws, and the question is how to get them. And there's of course a whole technology in quantum mechanics, beta ansatz and these kind of things. For classical systems, the magic tool is what people call the Lax matrix. Okay. So the Lax matrix is sort of an algebraic object. It's a matrix which at least you can look at, and which allows you to classify what are the conserved quantities. Okay, and that was a big discovery of Calogero. That no, this is too fast. No, I think it is the right order. Okay, so before explaining you, I wanted to show you a picture. This is I guess. Manas Kulkarni did this picture, so here's running time. If I don't know, 8 or 10 particles, and what you should see is that there is one fast particle. That's this one, which you can follow. You see that you have periodic boundary conditions. It's going like this. So this is sort of like a particle with a rather high velocity going in this background. But on the other side, if you think about the background, to think in this in terms of two-body collisions, doesn't seem to be. It doesn't seem to be such a sort of helpful thing to do, right? So there's still sort of it looks anyway. So It looks, I mean, visually, if I would do the same kind of picture for a non-detectable system, it would look much more noisy. I mean, so you have this sort of wavy structure, which sort of, okay. All right, so that's just for your intuition. Yes? No, you don't. I mean, well, I mean, you know, the solitons are the particles, right? I mean, so the lines, this is what I emphasized, right? I mean, I don't have any superstructure and sort of, you know, out of which I make sort of solitons. No, you should think of these trajectories as trajectories of, you know, in that language as solitons, right? But you see what I was suggesting in the scattering picture is that I can understand sort of the dynamics on the level of two particle scattering, which, you know, when you look at this picture, right, I mean, it's not completely clear what you mean. Okay, so now let's do this lax matrix, and so here you know, I just written down some concrete formulas so that you see that it's not only talking. I mean, so here is the lax matrix. So I have n particles on the real line, and so on the diagonal you have the momenta, and basically on the off diagonal you have sort of like the square root of the potential, right? And then there's this famous I here, which was historically. You know, people very often looked for real lax matrices, and they somehow couldn't find it. And then there was one big insight of Coloccio. No, I mean, you really have to look at also, you know, complex entries, and then everything works very nicely. Okay. So now the point about this, so you should think of this, you know, for every configuration I have this particular matrix, and since eventually, you know, my configurations will be sort of random. I mean, this is sort of actually a random matrix. It's fully occupied, but you see, I mean, it's sort of concentrated near the diagonal because, I mean, this has an exponential decay. Now, out of this lax matrix, I mean, you can form, you can write down another matrix which is called M. I mean, then together you have two, so you call it the lax pair. And they satisfy this sort of very important relation. I mean, so the point is that I evolve you know, I evolve the arguments according to the mechanical equations of motion. So this is what I mean by dTT. I mean, so this is just Newton's equations of motion by which I evolve the Q and the P. But then the point is that for that very particular object, it so happens that it can be written as terms of a commutator. And that's, of course, a very special property, right? If you out of this 1 over sinh squared, I do something slightly different, will not be satisfied anymore, right? All right, now once you have this, then when you look at this equation, then you realize that when I look at the eigen, it's a symmetric matrix actually. So when I look at the eigenvalues which are real, then these eigenvalues are not changing in time. That's just a simple consequence of that equation. Now, the eigenvalues depend on the whole configuration, right? I mean, so there are certainly highly non-local quantities. I mean, if I change a little bit, then the eigenvalues will sort of, you know, change around. And so you know, I'm sort of keep going to emphasize the notion of locality here. So let me make one trivial example so that everybody understands what I mean by local and non-local. So if I take the sum from j equal 1 up to n of pj squared, that's the kinetic energy, that's a local quantity, right? Because, you know, at index j, I just have one single variable, or maybe, you know, it could be slightly more complicated, but let me stick. But now, of course, I can make a non-local quantity when I take simply the square of that quantity, right? Then if I do the square, then I sum over all pairs, and that's highly non-local, right? And so what I want to say is that these eigenvalues, you know, they are functions on phase space, but, you know, they behave more like the square. I mean, you know, when I change a little bit over here, the eigenvalue will not depend, just sort of, you know, anyway. Okay, so this, but then people understand since a long time that it's very easy to make out of such a non-local thing something which is local, and the local is that rather than looking at the eigenvalues, you look at the traces of the nth power of the lax matrix. So that's the sum of our eigenvalues, right? And so this is what I did over here, and so let me just go through this line here. I mean, so here I want to define the nth local field at the position x. So first of all, there has to be a particle at that point. So this is why the usual delta function appears here. And then, you know, it's a local, it's a density of the conserved field, which is attached to this index j. And since the global one is the trace, I mean, I just take the jj's matrix elements of the nth power of that matrix. Okay. And then you see that things works out. I mean, if I integrate this, so this is the local one, and I get sort of the integrated, which is the total one. Then I integrate the delta function, and then I do the sum, and then you see it's raised L to the n, and that, of course, is something which is conserved because it's a function of the eigenvalues. But you see, this quantity is really sort of local because, you know, the point, I mean, the delta function is certainly local, and the L to the n is sort of a matrix which is centrally diagonal, and so this is sort of a quasi-local quantity. And then you look at this expression, and then, of course, you find that when I put here just the constant function, then this will be the particle number. And if I take the trace, I mean, that's the diagonal. I mean, then you see that I pick up the p, so that the first moment, so to speak, is the momentum. And then, you know, when I take the trace squared, I mean, then I get p squared, and I get the squared of this potential. I have to sum over everything so that you get the energy, and then you get higher order conserved quantities which have no name on anymore. Right? I mean, so that sort of works very nicely. And also, so this you forget. I mean, there's a second Lagrange matrix, but I don't have much time to say on this. Okay. Now, you know, was your question? You know, you might ask whether the collateral model actually also has solitons in the sense of an excitation where many particles involved, but which is sort of stable. And so for this, you have to ask Manas. So he has written a paper about construction of 1 and 2 solitons. But nobody has sort of done really the, you know, the soliton-based hydrodynamics of the collateral model. But there is such a thing, right? All right. Okay, now we want to do thermodynamics. Okay, thermodynamics is e to the minus beta h. Okay. Now we do the same thing over here, so I put here up wish lists. You know, I'm not able to go any much further in this whole thing, but I want to give you an idea what I really would like to do, right? So the first thing is you want to do thermodynamics, so you want to have, you know, want to confine your system spatially. So your first idea, which you learn in your class in statistical mechanics, you know, put periodic boundary conditions. Okay, so I put periodic boundary conditions. Okay, this you can do. I mean, the people have done this in the literature. I mean, then you know, you get a potential which is sort of the periodized potential on the wing. So you have these particles on the wing. In fact, there's still a Lax pair, but now you realize that this Lax matrix is actually much more complicated. And so already at that stage, I mean, you know, it's not completely clear, you know, and of course, you know, it's still conserved, but it's a much more complicated object. So let's maybe just stick to you know, maybe just, you know, the periodized Lax matrix. I mean, that's of course no longer a conserved quantity, but you know, for the purpose of thermodynamics, it's clear that your construction, you know, the way how you put the boundary conditions sort of is more a computational thing. And if you make the system very large, I mean, then it should not depend on the boundary conditions anymore. So we are doing the same spirit over here. So you see here, I'm putting sort of the formula which sort of, you know, what you would think in terms of statistical mechanics. I mean, you know, if you go back to Gibbs and then you think of how you write down your grand canonical ensemble, you see that it's a linear combination of the conserved quantities. And so, you know, if angular momentum happens to be conserved, I mean, you just add it to that list, right? Or if some particular system, which for some reason, two-component system, you also add it to the list. Well, now I have many of them, and so you just add it to the list, okay? So for each one of the conserved features I told you, I have its own sort of chemical potential, and then I do this sum over here, okay? So now, of course, it's clear, you know, for each conserved quantity, you need something which sort of, you know, it has a thermodynamic correspondence. But now you realize that, you know, this is a trace of L to the n, and now you see all this mu n sort of basically define for you sort of a power series of a function which I call capital V, right? And now there's unfortunately some confusion here in terms of notation because, but I was happy. I mean, yesterday when I saw the active system, I mean, they have the same problem. So when I talk about this potential here, you know, it's a potential, so to speak, in velocity space. So, you know, I talk about this as a confining potential, but it's not confining in space. I mean, that comes from the periodic boundary condition, but it's telling you that the conserved quantities should not be too large, so to speak. And so You know, you can think always in terms of the simplest confining potential, which is simply the quadratic potential. Then you see, then you only get L to the power 0, 1, and 2. And then of course, you know, it's the usual thermodynamic state. But if I now do the generalized thing, then, you know, rather than just having a quadratic polynomial, I can have some more arbitrary function, let's see, fourth order or whatever you think about. But what I emphasize, it's a function, right? So the point is that your thermodynamics depends now on the density. I mean, that's a scalar quantity, and then on a full function, or if you want so, on this infinite list of chemical potentials. But you should think of this really as a function, you know, power series of a function, and this function should sort of go up to infinity. It just means that very, very values of the conserved quantities are suppressed. All right?
Sorry, if I might ask.
Yes?
And the resulting free energy is convex, so to be?
You would hope so. You will see in a second. I mean, okay, but well, I mean, the way how it's written is the sum of exponentials, right? I mean, so the same thing which you teach your students, that it's convex. I mean, it's also convex, right? Okay, so now what you want to do? Well, I mean, you want to do the infinite volume limit. I mean, so I write down the partition function with this thing, and then the 1 over n, and then here's the normalization. I mean, I guess nu is the inverse density here. And then you get a free energy, and this free energy hopefully would be convex, right? Well, it is actually convex, but okay. Now I just want to remind you quickly of the ideal gas. I mean, then of course you don't have all these fancy interactions, and then you know what the generalized Gibbs state. I mean, the GGE would be it's just a product of these exponentials. It just means that your velocity distribution is no longer Maxwellian, but you know it's some general one particle distribution. Of course, such kind of a state is invariant under the ideal gas dynamics. And so we have sort of a rather complicated, but we have sort of an analog of this situation. All right, so fine. So I'm still working on this wish list, right? I mean, so I would like to show that this is actually case, but actually, so the real important thing is actually, I mean, free energy, of course, is important, but sort of it's a first order derivatives of the free energy, which are actually sort of the physical relevant quantities. So so these are the densities of the locally conserved fields, and you see that I mean, you know, if you sort of want to combine them, then the natural object to look at is actually the density of states. I mean, so you see the L is now a random matrix under GGE. So I distribute the P and Qs according to one of these generalized Gibbs, and then I look at the eigenvalues. And then I look at the density of states. I mean, this of course is a random quantity, but hopefully there's a law of large number, and which tells you then that you know, for large n, I mean, this will go to a deterministic limit, and this is a function. I mean, it's a real valued function, and it's a function on a real line. That's what I wanted to say, and you know, fluctuations are suppressed. So this is a deterministic quantity. So in some sense, if I give you, you know, what is the density, and I give you this confining potential, then you should somehow be able to compute what is this density of states. Now, why is the density of states so important? Well, I mean, the density of states is so important because, you know, whenever you want to compute, you know, the average of the locally conserved fields. I mean, so let's see the average density or the energy per side or momentum per side and all these things. I mean, they are basically moments of this density of states. So if somebody tells you what is the density of states, I mean, then in some sense you know all the thermodynamics of the system. Okay. Now let me sort of come to one of these sort of pictures which I sort of wanted to explain you what is this hydrodynamic scale. So now I'm thinking, you know, of initially putting some random initial data which have the property that you know, these conserved fields are not changing too quickly. So I can think of little fluid cells, and each one of these fluid cells I have one of the GGE. Okay, and so now I evolve this system, and of course, you know, what you're going to see is something which is pretty random, right? I mean, you know, of course you can see. You can record all the position and moment of the particles, but you will now see no structure. And so, of course, what you learn is that you know, if you want to see hydrodynamics in a real fluid, I mean, you have to distinguish between, you know, sort of very quickly, fast, microscopic degrees of freedom and those which are slowly varying. Now, of course, in the usual hydrodynamics, I mean, you know, it's physically very obvious and natural and studied since many years, so you know what to do. Now, if you now come to this somewhat sort of strange animals, you don't really know what to do. But you see, what I'm trying to tell you is that the filter which sort of filters the slowly varying quantity is the lax matrix. You see, so what I have to do is I evolve this up to some time t. I don't see anything, okay? But at that time t, I record all the let's see, I'm thinking about a little fluid cell over here. So at this particular time, in some spatial region, maybe 1,000 particles. And now what I record is just in this little cell, I record the position and the momenta, okay? Now, I plug this into my lax matrix. I turn on my computer, and it spits out, the eigenvalues. Now, with the eigenvalues, of course, there it's still sort of changing quickly. Now I form the moment, so I form the density of states. And now the assertion is that the density of state is the quantity which is sort of evolving slowly in time and which solves a closed equation. So in that sense, so the lax matrix sort of works as a filter, right? It filters from the many degrees of freedom which I have, decreases those which sort of, survive on the hydrodynamic scale. All right. Okay, so now this is sort of the only sort of slightly technical part here of the talk. Maybe I'm looking at the watch and cannot do too many. So okay, so what I'm trying to write down here is the way how you actually derive what is this density of states, right? So maybe actually I will skip many of these illuminating remarks here, and I just want to say that I'm sort of going to. Okay, so I want to. Okay, maybe I should say this. So I want to sort of compute this partition function. Originally I proposed to have periodic boundary conditions. I don't know what to do. Periodic boundary conditions, I write down the formula and that's the end of the story. But now you say, okay, what I learned also is that sometimes it might be good to just put an external potential. So maybe a potential which goes up very quickly here, right? And so this actually works, and the way how it works is sort of displayed here in these formulas. But let me just summarize. The point is that there's sort of an algebraic machinery which you can turn on and which allows you, if I make sort of the correct choice of this external potential, which allows to sort of actually do rather explicit computations. And so I just want to emphasize one point here. So I cannot possibly explain this in any detail anymore. But what I want to show you this one formula, and it comes completely out of context, of course, but here is sort of, I can do some integrations, and this is sort of an intermediate partition function which appears over here, right? So the lambda you should think of, but what I'm trying to say is that I want to compute the density of states, and of course, one step in order to compute the density of states is to first compute what is the distribution of the eigenvalues. Okay. Now the assertion is that with this particular boundary conditions, which I don't want to go into. You see here a formula which tells you it's an exact identity, which tells you that what is it? So lambdas are here the eigenvalues of the lax matrix. Now I've written here that as an integral, but forget about the integral. I'm just saying that under the GGE, the distribution of eigenvalues is given by this rather explicit formula. So here you have, this comes because I'm working now with the eigenvalues. So this is sort of this confining potential that's sort of given in terms of my formulas. But here there's a sort of a more complicated interaction, right? So since I haven't told you what is the K0 and all these things, it's not so important. One thing which I found very surprising, sort of, which I wanted to explain in these things, you ask yourself, what kind of statistical mechanics problem do I get? And to the big surprise, the statistical mechanics problem which you get is actually a mean field problem. It's not very transparent from this formula yet. And what I mean by mean field is that when you look at the exponential of when you look at your Gibbs exponential, this object over here, it can be written as a functional of the density of states. You see, usually if I think of a nearest neighbor Ising model, I mean, then of course it cannot be written as a function of the density of states, and then you get some thermodynamics by some other means. But if I make a mean field model, you know, with a 1 over n and something, then you know, you write explicitly your Hamiltonian as a function of the density. And the surprising element of this formula is that after doing this integration, I mean, you get something which can be understood as a mean field type model. And therefore, at the end of the day, you actually have a variation formula. So I just wanted to display this thing. I mean, so the assertion is that despite the fact that things look so complicated, at the end of the day, your free energy can be written in terms of a variational problem. And the variational problem concerns only a function which is living on the real line. You see, I mean, you have variational problems which live in very large spaces. I mean, they are sort of, you know, of course you can write them, but they're not necessarily so useful. But here, the point why it's extremely concrete is that you know, you get this kind of free energy function. And so I just want to show you some of the terms which you know already. This comes from the confining potential. I mean, so this is sort of, you know, just independent particles. I mean, it's just linear, and this is density of state. I mean, you know, this just comes from the diagonal, so to speak. And you know, if I would remove all the off diagonals, and I would ask myself, what do I see? Well, then of course, you know, it's just an you know, a matrix which the entries are IIT, so that everybody can do. I mean, so I get this term, and here, of course, here you see the entropy term, right? It's the rho log rho. So this you would have if I just turn off the interaction. And now if I turn on the interaction, I mean, you get something which is sort of somewhat more complicated in the sense that, you know, there's this log and there's 1. Here's the density of state, and now comes sort of this, what I call here the function, this function phi Calogero. Okay. And the big surprise, I mean, okay, so I have to go back. The big surprise is that this Calogero is actually computed on doing, you know, this elementary 2 particles shift. So you see, the main point is that in your free energy, suddenly, you know, without suddenly, I mean, this dynamical quantity, namely, which is so basic for integrability, appears in the free energy function. Okay, and then if you want to write down your hydrodynamic equation, then you know, they have the sort of the standard form. I mean, so they're usually written like, you know, the local density of states at the space-time point x. The W is the function which gives you sort of the local density, which is now a function, a smooth function. And now I've written down here the conservation law with something which is people call the effective velocity. You know, if I write it down like this, of course, I can always write it like this, and you know, be effective with some complicated function of rho. I mean, so this is sort of like an almost empty statement if I just write it down by itself. It's just saying that, you know, this quantity satisfies the local conservation law. But the main point, I mean, this is the discovery of 2016. The main point is that you know, you can actually write down a formula for this V effective. If I leave off the interaction, you know, then I would just here would be just W, and then it would be just sort of you know, the somewhat trivial Euler equation for an ideal gas. But now I get sort of this whole correction term, and you know, you see that what I have to do is I have to solve a linear problem. So, you know, I have given locally what is the rho. I mean, this is sort of the same object which appears over here. And in order to know what are the currents, I have to solve this linear equation. And that was a big discovery that you know, this you can do on a computer easily, and so you can sort of numerically solve this hydrodynamic equation, and you can do a lot of predictions on that basis. Okay, so I'm sorry, you know, I'm sort of jumping over many things, but I want to give you at least some sort of impression.
Just one question. No, so in F up there, everything seems to depend only on W, but in your hydrodynamic equations, for each W, there's a field rho, right?
Yeah, it's sort of like
there, where is the field? I mean.
No, okay. So it's like for a real fluid. In each little fluid cell, you will have a definite temperature, density, and okay.
And that F pertains to each point X up there.
Wait a second. Where are you? Are you here?
No. So if you go back up to your F.
So this is now the free energy function now.
Right. It's a functional of rho.
Rho. Rho is the density on the real line. Rho is the density of states. rho is the density of states. You see, what I'm saying is that in the infinite volume limit, you will get a variational problem for the density of states. Of course, you know, when I look at the finite system, the density of states is fluctuating, but it's fluctuating not too much. And if I take the large n limit, then the fluctuations go down to 0, and what I'm left over with is a variational problem as written over here. So if I want to know what the free energy is, I have to sort of minimize this object, and the minimizer is the density of states, which belongs to that particular thermodynamic parameters, which is the density on the confining potential. You see, so what I have given to you, what I have to give you is that the thermodynamic parameters in this formula is the V, and the density is sort of somehow, anyway, the density is the density is actually sitting exactly up here. You know, this function is positive, and it's normalized to the density.
It's a state of the internal states.
It's an internal state. It's a state of the particles. Yeah, it's a density of. Well, it's a density of states of the Lax matrix, right? I mean, so if I give you the P and Q, and then of course, you know, it depends on what are the thermodynamic parameters, right? If I change the temperature, of course, I will see a different density of states of the Lax matrix, and this formula tells you what is the connection.
Okay, but then the conservation laws for the rows down here, your hydrodynamic equations. I'm sorry, I'm just missing something.
No.
X and T for each W.
Okay, so now okay, so this is a pure statics, right? I mean, so it's a completely homogeneous system, just a static one. Okay. Now of course I make a big jump. I say that once I understand the statics, then I can also sort of, you know, by making sort of the assumption of local GGE, I can also write down the hydrodynamics. I mean, it's just how you would.
You're applying that thermodynamics pointwise, or
so you see, okay.
At each X.
That's right. At each xt, that's right. But so the main point is that you know, so here, you know, what I have to do is, so here, you know, I assume that you know, in this cell I have a well-defined density of states, right? But now if I want to do the next time step, I have to know, you know, according to which velocities that's actually moving. So you see, I give this one, so this appears in this integral equation, and then the assertion is that I have to solve this integral equation, which gives me the velocities, okay, at each xt. And then, you know, I have to sort of solve this for one little time step, then I will get a new density of state, and then, you know, for each xt, I have to go through this formalism again, right? I mean, so this is what it's saying. And so you see that you know, and so I mean, you know, eventually you will get sort of like you know, one particle, you know, a function in one particle phase space. You know, I have xt, and then there's this extra variable which, you know, for the non-interacting case would have the meaning of a velocity, but in the interacting case it sort of becomes the density of states. All right. Yes? No, I understand. Well, what's the question? I mean, so you look at this free energy function?
Like usually the dynamic fluid, the interaction scales like n squared.
Yes.
Whereas the entropy scales like n.
Yeah. Okay. Good point. Okay, so you're thinking about. Okay, so let's just repeat the question. I mean, so when people look at GUE, let's say, I mean, then you know, sort of traditionally. You look also at the large n limit, but you make a scaling in such a way that you know, everything is energy dominated and the entropy is the small convection term. But you see here, I have no choice, right? And the answer is no. I'm sort of, you know, what people call high temperature in the context of random matrices. I mean, you see that this log and this one are sort of living on the same scale. Yes, correct. Mm-hmm.
Does it happen sometimes in this context that conserved quantities and many conserved quantities correspond to Noether charges?
Good question. I really don't know the answer. Yeah. Well, I mean, maybe there is. I mean, people are sometimes telling me. I mean, sort of, at least sort of in the way I'm setting up here. You know, I have the densities of the conserved quantities, and yeah. I'm not. Yeah. Okay. I just said no.
There's no symmetry of the Lagrangian.
Well, not really. I mean, there's no real. No, there's no real Lagrangian. I mean, anyway, so yeah.
Okay, one last question.
Yeah, okay, thank you, Herbert. Just to be sure that I understand, so this rho of W is the density of states of your random
the
lax matrix, right?
Correct, yes.
Under the GGE statistics.
So the GG tells me what
Yeah,
is it,
sure.
what is it, yeah.
What would you expect about local statistics of such matrices? Do you have any hint, any guess?
That's a good question. That's a good question. Do we know Manas? We don't know. Where's Manas? Do we know?
Expect
Not
the
really.
sign
I mean,
kernel
no, I don't think sign kernel or anything like this. So what? Okay, so maybe I can answer that sort of in the following way. So you see. So here you see this log of 1 plus W squared. I mean, that just comes out of the mechanical problem, right? You see, when you do the total lattice, actually the 1 disappears and you get just the log.
Okay.
And then it's actually really the log gas. And it's really the log gas which you know from random matrix theory, right? Now, you see here, yeah, it changes, and now I get the random matrices, which sort of, doesn't seem to be easily connected. I mean, there's also other models where there's a connection between the Lex matrix and the circular ensembles. I mean, so it's actually the density of states. It's actually the Lex matrix is not a symmetric matrix, but it's actually a unitary matrix, right? I mean, and that so in some models, I mean, you have a direct link to random matrices, but otherwise, yeah, you see it's sort of like a log gas which has been sort of slightly modified, right? I mean, but it has never appeared in the random matrix context.
So it's not even clear that there is some universality there.
No, okay, so to me, not to me, the universality is that okay, so this two-particle scattering shift depends on the specific model, right? I mean, here you get the log. I mean, if I do the delta Bose gas, it's the Lorentzian, and this is really comes from model to model, and then it's sort of a little bit accidental, if you want. So, but of course, what is general is that the way how this quantity, I mean, this scattering data enter into your free energy, that's a universal phenomenon.
Okay. Thank you.
Okay, thanks very much. So we thank Herbert for this.
Okay. I still have 3 slides to show, but I mean, that's okay. No, I was just interrupted by questions, but it's okay. No. Just right. No, that's just perfect. I don't mind. No, there were some conclusions and all kind of things. No, but don't fear. It's okay. It's okay. Actually, it was a good end because you see, I mean, people were looking and they really had questions on that. I mean, so I think, no, it's just perfect. Yeah, okay.
Okay, so the next talk is by Tridip Sen from Mumbai, and he's going to talk to us about large deviations in non-equilibrium steady states of diffusive systems.
Okay, thank you, David. So in this work, we revisit a rather old problem that almost everyone in this audience have encountered once in their life. This work started almost 10 years ago from Ori Hirschberg. He was really interested in the effect of slow boundaries. And then almost 10 years later, almost in 2020, we looked into this model from a very different, more technical perspective. And there was a microscopic derivation of these results were derived in collaborations with Bernard and Ori. And very recently, last month, we put a paper which analyzes the same problem using a hydrodynamic theory. So I'm going to tell you what these works are about. So let me start by telling you exactly what it is, what this work is all about. So it looks at this question that almost 3 decades ago people have been looking at, is that if you take any system where there is some kind of transport of energy, particle, spin, or anything, and they are interacting, and then there is some kind of dynamics inside, and you couple with 2 different reservoirs. They could be particle reservoir, energy reservoirs, or something else. And now if the 2 reservoirs are at the same chemical potential or at the density, the system at large time will be in equilibrium, and we more or less know what to do there. Now, the interest comes in when the two reservoirs are at different densities, then at large time, the system reaches a stationary state where there is a non-zero flux, and the system is in non-equilibrium stationary state. And the interest is, how do we characterize or understand the fluctuation in this non-equilibrium stationary state, particularly its macroscopic properties. So the idea is that you coarse grain, look at the system at the largest, like a hydrodynamic scale, look at those fluctuations, let's say, of those densities around the average typical profile, and how do we characterize those fluctuations? It's been traditionally, there are two quantities people have looked at to this kind of problems. One is that in that non-equilibrium stationary state, what is the probability of this coarse grain, let's say, density profile? And normally you can write it in this kind of form, which is reminiscent of the Gibbs distribution. Okay? The other quantity that people often looked at, that what's the net flux that has moved, let's say, over a time t. So what's the distribution of that current? And that also normally has similar exponential forms. And this you all know that these are these large deviation forms. The idea is that if you know these large deviation function, it would characterize most of the macroscopic fluctuations in that non-equilibrium stationary state. Now, in this context, there is two famous results from the early 2000s, which almost started these results of large deviation in extended systems. And these were about a specific model, which is this symmetric simple exclusion process coupled with two reservoirs, which is just continuous time random walkers with hardcore repulsion. Oops. Sorry. So, okay. So the two results were the following. So in 2000, Derrida, Lebowitz, and Spear, for that symmetric exclusion process, using certain microscopic analysis, they found an exact expression of this function. 4 years later, they also did a similar kind of calculations for the distribution of current and found an exact expression for this large deviation function. Almost immediately, there was a group in Rome, Bertini, Dessol, Gabriele, Genalosinio, and Lundin. They used a hydrodynamic theory to check that within that hydrodynamic theory, they also could get that same result. Okay? So they did it for both the cases, and this is now known as macroscopic fluctuation theory. Okay, so just to roughly tell you what was the interest in this kind of problems is that you draw analogy with equilibrium. If you take the system coupled with one reservoir, then you know that equilibrium StatMech would tell you that distribution of the profiles would be given by the Landau free energy here, and it comes from the equilibrium StatMech. Also, this gives you a bulk property in the sense that the fluctuations has some amount of robustness as long as the coupling to the reservoirs are localized to some extent. Now, then you ask the question in the non-equilibrium scenario, and it's not obvious that you're in the non-equilibrium stationary state, the distribution will have any such form. And there comes this theory of large deviations, which gives you one reasoning that it could be expected. The question that we asked is that, okay, so if it really plays the analogous role of free energy, then it must have some kind of robustness. Now, whether that free energy in the non-equilibrium stationary state is robust or not, that's the question we asked, and it was slightly non-trivial given the fact that there is a presence of long-range correlations. Okay? So we wanted to first understand in an exactly solvable model and see quantitatively what is that robustness. So for that, we went back and looked at this first model of symmetric exclusion process, and we make the perturbation in boundary by this following way. What we did, we changed the time scale of the jumps at the boundary. So it just, all the rates gets multiplied by this 1 over L to the power alpha. Alpha is some real parameter. You could see that if alpha is very small, then this is of, let's say alpha is 0, then it is order 1, that is similar as the rates at the time scale of the bulk, and that is the result that was done by the earlier people, the Bernard and others. So that is where you get the non-equilibrium state. And on the other hand, if you take alpha very large, then the coupling or the time scale becomes very slow compared to the bulk dynamics, and you would expect the system would behave like an isolated system, and that's what you get. But it turns out that there is an alpha equal to 1 demarcates these two regimes. So one is a non-equilibrium regime, another is an equilibrium regime. And the fact is that in both these regimes, each regime has its own unique large deviation function described in this entire spaces. So in that way, the large deviation function that Derrida et al. Derived, it has some amount of robustness. All right. Now, this is what I'm going to tell you about. So how do we really show this, this particular claim? So you can actually solve for all the, any arbitrary alpha here, but a nice way to see this is sit at this alpha equal to 1 point. So the way now we parameterize the rates as saying that is 1 over L, so alpha is 1, and I introduce this parameter gamma, and then I sit at that point and I look at gamma to 0 limit, where this becomes order 1 kind of. So that is the non-equilibrium regime. If you go gamma to infinite regime, that is the weak coupling regime, okay, or slow coupling regime. And we could solve this problem explicitly and look at this two limit, and you can see these two different fluctuation regimes. Yes?
What do you mean by equilibrium and non-equilibrium?
So the point is that in this regime, the fluctuations are governed by a equilibrium local free energy functional. Okay? All right. So just to give you the explicit expression, so the free energy functional of density for this arbitrary gamma parameter has an explicit form.
Understand.
Yes.
You still have two different, rho A and a rho B at the
Yes.
two ends.
Yes.
So the problem is still a non-equilibrium problem.
Yes.
Okay.
But in the scale that you are looking at, the fluctuations are almost governed by, so the fluctuation in this part, where you don't look at the fluctuation, anything that's happening at the edge boundaries, but the bulk fluctuations are that of the exactly like a isolated equilibrium system. Okay?
Is the current also vanishes?
It, in the scaling, if you're looking at, so I'll just show you that there is current result immediately. But the point is that you have a formula, and you can write it in this form. You can write it in even more explicit form, but this is one nice way of writing. The one thing that you immediately realize that this functional is non-local. So that represents the presence of long-range correlation, which Herbert, Christian have looked at time ago, and particularly this paper I came across when I was a postdoc, and I find this is a really remarkable paper. I encourage you to look at this paper. Okay, for the current, there is a similar kind of form. This is kind of a nice way of writing the formula. You can make it even more explicit. And the question that Avishek was asking, that if you now take the gamma tends to 0 limit, which is the fast coupling or the strong coupling regime, you recover the earlier results of Bernard and others. If you look at gamma tends to infinite limit, which is the very coupling, this expression will give you 0, but you can do the computation more explicitly for any arbitrary that alpha, and you would get this value, and they are compatible with each other. It's just the fluctuations are subdominant. Yes. Yes. So the free energy function of density indeed becomes local. Yes, and we can show it explicitly what it is. So everything is hidden in this particular two formulas, and you take the two limits and you would get those. It needs, not immediate, but you need to do a bit of analysis to get the limit. Okay, so Mustansi told me yesterday a story that C.N. Young used to always ask this question: if you have an exact result, how did you get the exact result? So I understand that there's some importance in explaining how do you arrive in those kind of exact results. So in the rest of the talks, I try to explain just to give a glimpse of how we arrive at these results. And then I'll give you another approach, which was this Bertoni et al.'s approach, which will then generalize this analysis to more a large class of interacting many-body systems. So that's the rest of the talk will go. All right. So, you have to, this problem of SEP is a really interacting problem. So just one way to see this is that this is a very well-known mapping that many of you probably know, that if you look at this symmetry exclusion process and this coupling, and you look at its Markov generator, it has a direct mapping to that X spin chain, the Heisenberg spin chain. Now, the coupling at the two end gives you some kind of non-Hermitian terms. And this has been noted. Deepak, Mustansi had looked at, Herbert has looked at, Gunter, many people have looked at. And for the out of equilibrium case, this non-Hermitian terms makes the analysis a bit more trickier. Okay? So you can see that because of this, if you do the Jordan-Wigner transformation, it also becomes a interacting fermion problem, now coupled with external reservoirs of two different kinds of chemical potentials. Okay, so there have been many earlier works. So you can look at these series of works which try to analyze this problem. But I'll first just give you a glimpse of how we derive the results. So let's first look at the current problem. So the idea is to map this analysis into the usual transfer matrix kind of calculation that we all do in our graduate studies, like the solving the Ising free energy problem. The idea is simply that if you have the process, this is a Markov evolution, then you can write down the probability at any final time as e to the power t times m. So this is the formal way. Now, if you ask what is the, let's say, generating function of this current, then because as the system makes jumps, each contributes to a value of the current. So there is a way to embed this counter into this kind of the Markov matrix. So that modifies the Markov matrix, and formally you can write it in a similar form. Now, if the Markov matrix has a gap in its largest eigenvalue, then you would find that this at the large time limit is dominated by the largest eigenvalue. So everything now boils down to finding the largest eigenvalue of this tilted operator of the matrix. Now, as you saw, that this matrix is very similar as now the XXZ spin chain with this boundary coupling. And what we are trying to find out is the ground state of that. And we want an analytic expression of depending on all these parameters. So typically, it's very difficult. So because what happens, usually you try to go into the particle sector decomposition, but now because of the boundary terms, different particle sectors are coupled, so there is a hierarchy. So in these cases, when things of such hierarchy comes, one standard way to do is do a perturbation theory. So what the idea is that we write down this eigenvalue equation problem in a low density perturbation. And because of some, I call it 4 miracles that happens for this problem, they are able to find this in a perturbation theory, the terms up to certain order in the eigenvalue. And then looking at those few terms, we are able to guess the full functional form. So I'm just going to just emphasize what is these miracles. First miracle comes is that if you look at a certain order, then it's a finite, the eigenfunction is certain finite polynomial. And then you can put it in Mathematica, play with the equation, and you start getting these eigenvalues. And I'm just going to show you just roughly how crude the eigenvalues look like. You go to the 4th order, it becomes unmanageable. Then you realize the second miracle, that there is a symmetry in the problem. So you invoke certain like parity symmetries, particle hole symmetries, and there is a symmetry which is related to the similarity transformation of this tilted operator, which is like kind of a Galois coherent. And once you combine this, and this was already recognized by Bernard, that this ground state wave function, all this parameter dependence comes through a single function, which is this omega. So you write all these 4 ugly looking order of eigenvalues, and you can now, if you think of it as a series in omega, this becomes much simpler. Even now, it's still difficult to guess. So you now realize that we are interested in the large scale behavior. So let's take the large n quantities. And that looks now up to the 4th order in omega. It looks a bit more tractable. So this L1, L2 has some parameter dependence, okay? But still it's hard to find a solution. So what you then look at, if you look at only the first terms, okay? So then the first terms has a much more nicer form. And then you immediately recognize this is the arc sine square root omega. And this was the Bernard's earlier result of the strong coupling. Once you realize it's the strong coupling limit, and then you think that what is actually happening in the weak coupling case, that there's a contribution coming from the bulk and the 2 boundaries, then there is a way to construct some kind of variational argument. And that, if we use that argument, then we are able to write down this series in a formula like this. Okay, so it incorporates the entire series, and once you guess this, you can numerically verify that the even higher order terms fits into this. So that's how we got the full cumulant generating function. So just to give you a glimpse of how the results were arrived. The second one is about the large deviation of density, which is a bit simpler. So the way it happens is that what you would usually do if you want to find out the free and Landau free energy, you will start with the Gibbs distribution and then coarse grain. But in this case of non-equilibrium stationary state, there's no Gibbs measure. But fortunately for this model, the stationary state is known, and that was due to the work of Martin, Bernard, and all these people. And it tells you that if you look at any configuration, then the probability of that configuration, you can write it as a product of like a string of certain operators and sandwich between 2 vectors. And this operators follow such kind of quadratic algebra. Okay? And this was the review article. While I was preparing, I remembered that In this room, when we were attending a summer school, me and few friends of mine, we were reading this review article sitting in one of those benches, one of these chairs. Okay, so the idea is that you will be able to write down the microscopic measure in the stationary state and then do the coarse graining, and you would arrive at this. And this is what this people, Derrida, Lebowitz, and Speer, did it in 2000. Now, that calculation required certain specific regimes of parameter, now choosing something like alpha plus gamma equal to 1 or those kind of properties in order to do this calculation and do the coarse graining. So that turned out to be a bit difficult, but we found another way which I feel is more intuitive to arrive this weak coupling result problem. And the idea was this following. Okay, so what we recognize that if you take this weakly or arbitrarily coupled system, so this is the arbitrary coupling parameter, there is a direct connection to that of an extended system which is strongly coupled. Okay? So you take an extended system and look at the same intermediate portion of it. The fluctuations of the extended system which is strongly coupled is exactly same as the fluctuations of this weakly coupled system. And that you can establish rigorously by showing that there is a direct relation mapping between all cumulants to any order between these two systems. So once you recognize this, then the problem is easy, because I can now use the earlier results of in the strong coupling limit. I look at their fluctuation, and then I integrate out the fluctuations at the two ends, and that should give me the fluctuation of this weakly coupled system. So this, at the hydrodynamic scale, it means you have the fluctuations for the strongly coupled system. You integrate out the fluctuation at the two boundaries, and you get the weakly coupled system density large deviation. It is still requires a bit of work because this functionals for the strongly coupled system is still non-local. So you have to do a bit of calculation to arrive it. But that's how we arrive the result that I showed you. Now, again, so what is the point of these exact solutions? So for me, the point of this exact solution is that it allows me to test or do a benchmark of a more generally applicable approach, which may not be as rigorous as this, but it would cover a larger class of system. And that is this fluctuating hydrodynamic approach. So in the rest of the talk, I'm going to explain to you how you could get back all these results that I discussed using the fluctuating hydrodynamic approach. Now, when we first wrote the microscopic paper, the referees pointed out that the results are important because they falls outside the regime of the macroscopic fluctuation theory. And the idea was that the fluctuations now gets dominated by the single bonds at the boundary. And naively, you would expect that if you're doing a hydrodynamics, the single bond effects will not be captured. But that is not the case. You just need to do a careful analysis, and things all comes correctly. So this is what I'm going to explain to you, how you can get the same result through the hydrodynamics. Okay, so just to give you an idea of what is this fluctuating hydrodynamics is about, the idea is simply that rather than looking at every microscopic occupation and microscopic state, you look at a coarse grain scale and replace all those occupation of each particle position by a coarse grain density profile, something that Herbert was talking. And then the idea is that you look at the evolution of this coarse grain density profile, which will be stochastic. Now you talk about how this different evolution of the density profile, what is the probability to see each such trajectories? And the idea is that such evolution of this conserved charge and the associated current will be expressed or characterized in terms of some kind of action. Once you know the action, then you will be able to describe all these properties at the hydrodynamic scale. So that is roughly the picture. And that was the idea behind this macroscopic fluctuation theory, is to able to describe even at the fluctuation level at the hydrodynamic scale. Okay? Okay. So now often the difficulty comes in how to derive this fluctuating hydrodynamic theory, or rather to get to this action. There have been many different ways that people have tried. There are more rigorous approaches. There's approaches through invoking this idea of mapping to the quantum spin chains and doing this coherent state path integral. You can also try to argue by somehow arguing the fluctuating hydrodynamic based on physical reasoning and then doing Martin-Sigia-Rose kind of formalism. We found that there is a bit more simpler, which is also a bit more intuitive to me. There is another way of doing this hydrodynamics, which goes back to Lefebvre and others. So you start with the stochastic dynamics, then you define some kind of microscopic action, and then at the microscopic action level, you assume that there is local equilibrium. What this means is that your system has some local equilibrium, or the fluctuation is governed by like local equilibrated system with very smoothly varying chemical potential. So you would have to average this microscopic action with respect to that smoothly varying chemical potential distribution. And then once you average and you write down in terms of the large scale fields, you will arrive at the hydrodynamic action. So if you want to learn a bit more about it, Shomo Broto, who is here, he has a poster outside and he can explain to you how to do this cleanly in certain systems, particularly for the case of SEP. All right. Okay, so now what is that action? How does it look for the case of symmetric exclusion process? Sorry, okay, so this is how it looks. So what you look at is that you want to write down that action in terms of the conserved charge and its current, but typically it's more convenient to write in terms of the conjugate variable of the current, which we denote as rho hat. And if you look at the action, it has this kind of Lagrangian structure. It's like PQ dot minus H. Okay, so rho hat behaves almost like the momentum field. And the H is something nonlinear. Because we are looking at the system which has this weak coupling at the boundary, for this problem, the Hamiltonian has a bulk part and the contribution that comes from the effect at these single bonds at the boundary. Okay? So this describes the evolution of the hydrodynamic, at the hydrodynamic scale, evolution of this, let's say, the symmetric exclusion process. All the probabilities of the trajectories are characterized by this action. Okay? Now, given this action, how do I now get back or reproduce that result of the large deviation of density? The idea is quite simple because all you could do is simply the saddle point. So if you want to look at what is the probability of an atypical fluctuation from the deviation from the most typical one. So what you would do, you would look for all the paths that could create a start from the typical state and end up at this atypical fluctuation. And the sum of probability of all possible trajectories gives you that probability. Okay? So this would formally would come like this kind of path integral. Now you realize that the action is extensive in the system size. So the simplest thing you would do is do a saddle point, and the saddle point will give you the large deviation function if there is a unique saddle point. Okay? So in this particular problem, there is a unique saddle point. And so in this calculation, everything now boils down to finding this least action path or solving the Euler-Lagrange equation. So for this problem of SEP, if you look at, start with that action, the Euler-Lagrange equation looks like this. So this is the equation for the coordinate field, and this is the momentum fields. And there are a couple nonlinear equations. You have to solve it with different boundary conditions. So the temporal boundary condition for this is just you start with the most typical state and end up at the fluctuating state. Now, because we are looking at this weakly coupled system, there are additional boundary conditions that comes at the spatial boundary, and they look rather ugly. Okay? Now, I should make a comment here that there has been recently some very interesting development from the work of Pierre Ledussal, Baruch Meeson, Kion, and Sasamoto, that they found that this equation has a connection to an integrable model, which is called AKNS, which can be also solved using the inverse scattering method. But although in principle you can solve it, you can really do it in practice for very specific observables, particularly that of a current, where the boundary conditions are much simpler. So that is for an infinite system. This is also, in fact, this is for a finite system. You have additional boundary conditions. Now, if you had looked at the strongly coupled problem, that was a problem. In that case, the boundary condition was almost very trivial, that the rho hat is 0 and densities are fixed. Okay? This problem was studied by Jorge Kuchan, Vivian Lecomte, and Julia Taylor in 2007, okay, which was the strongly coupled system where this boundary condition is really simple. And they managed to solve it by finding a two-step non-local transformation, which maps this problem to an effective equilibrium problem. Now, if it reduces to an effective equilibrium, you know that the large deviation function is the lambda free energy. So you know that, and then you map it back and you get the result. Okay? But what if you try to do that for this ugly looking boundary condition problem, it gets very difficult, okay? So what we managed to do it is that we actually solved it by a single local transformation, and this is the transformation that I write it here. I make a change of variable from rho hat to a new field f. And then you play with the equation, and you can see that the problem, even with that ugly boundary condition, could be solved. The solution is simply given by that the f field satisfies a backward time reverse diffusion equation with a Robin boundary condition at the boundary, the spatial boundary. And this solution is fully self-contained. Once you know this solution, density at any time in the evolution is simply expressed in terms of that f function. Okay, so this comes after a bit of algebra, and this is how you solve this ugly looking boundary condition problem. Yes. 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 Right. So I want to look at the fluctuation of an atypical profile, which is R of x. And I want to, the large division characterizes what is the relative probability weight correspond to a typical state. And the typical state is rho bar. So all that I need to know, all the transition paths that started at rho bar and it ends at R. Now I need to do it at an infinite time because the rho bar is a fixed point. Okay? If you want to say that I wanted to see it in a finite time, that doesn't give the stationary state result. Okay? So this two just put by hand. This boundary condition simply emerges from just minimization of the action. Okay? So unlike in the strong coupling where people put the boundary condition by hand, here it's nothing like that. It just comes out of the action. And that was our main reason of looking at this weakly coupled system, because we were uncomfortable in putting that boundary condition by hand. So now everything comes out of the calculation. Yes. It does depend. It says embedded, all this rho dependence, gamma dependence. So this is on the left side. There is a similar ugly looking boundary condition on the right side. I just didn't write it for this. Okay? All right. So if you put it now in the minimal action, do the algebra, and you get back the microscopic result for large division that you showed. The advantage of this procedure is that it actually tells you how does those fluctuations get created, that in the path towards that particular fluctuation is fully contained in this solution. Just to demonstrate that you can really do it, these are just the plots from our exact solutions, that you start with a typical profile, and you want to end up there, and this is just intermediate some density profile of how those fluctuations are created. So this was not available in the microscopic analysis. This only comes out in the hydrodynamic theory. Okay? Now the second part, how do you do it for the current? Very similar story. Yes? Any rho bar. It has to be, in this case, when you're asking the question of large distribution of density, it has to start from the typical state. Yeah, as long as if it is a stationary state, then we can choose in anything. Okay, right? Because there's a rho bar of x actually. So I'll come soon to a more general systems. Now comes to the question of current. The same story comes that once you know the action, the calculation of the large differential function of current boils down to finding these classical paths, or rather solving the least action paths given of the action. So let's say you want to find out this cumulant or the generating function or the Laplace transform of this distribution of the current. In the path-identical form, it would look like this, where this term I have absorbed into the action. So that now my S has extra parameter lambda. And then you do it for the large time, what would happen, or large system size, then you'd find that this gets again dominated by the saddle point, and this saddle point gives you the cumulant generating function of the current. All right? You can show that you can formulate similarly, write down those equations. In this case, you can argue that the optimal profile or the least action paths are predominantly remain stationary, except some small dependence at the two end, but those are subleading. And if you use that, then your Euler-Lagrange equation, which is now time independent, looks this kind of form, which is again a coupled nonlinear ordinary differential equation. And you wonder, how do I solve it? And also it has, again, a similar ugly-looking boundary condition. But this can also be solved. And then at the end, you can write down this optimal path in a parametric, nice-looking form. And this is, again, it tells you not just it not only recovers the microscopic result for the current, it also tells you what are those optimal paths of creating towards those large fluctuations, okay, or atypical values. All right. This is just a way to show you the cumulative generating functions. Okay. Now, I try to motivate that the advantage of this hydrodynamic approach is a bit more general. That you do not always need to look at every microscopic, those models, which are very, like often they depend, they're quite fragile because you sometimes require these ideas of integrability or beta integrability kind, and so in order for their solutions. But I can now, this hydrodynamics formulation, the idea is that it would apply at the hydrodynamic scale for a wider class of systems. So I'll give you a couple of examples. So the simplest example that I would give, just take the same symmetric exclusion process, but now change the threshold height to something larger than 1. So in the standard symmetric exclusion process, you allow at most 1 particle. Now in this case, I would allow, let's say, 2j number of particles. So this one studied by these people and also emphasized by Kushan and recently by Frazek, Giardina, and Kushan. So now, if you look at this particular problem, it has, again, a similar spin chain representation of the Markov generator. But it now looks at similar like a Heisenberg, but it's a larger dimensional representation of the SU2 groups. And this is microscopically non-integrable. Okay? But if you look at it, do the similar coarse graining and look at its hydrodynamics, it looks very similar to that of the standard symmetric exclusion process. And you can do the same machinery and get the large deviation function. So even though the microscopic dynamics is beta non-integrable, at the hydrodynamic level, the analysis you can fully do, and the hydrodynamic equation looks like those integrable equations that appear in the symmetric exclusion process. How much time do I have? 10 minutes, okay. All right. There's a similar model, which is this model of heat conduction. This was also studied a lot in the context of large deviations. This is a model where you forget about momentum conservation. So the particles are coming, hitting, but they're exchanging their energies. So your dynamics preserves the energy, but the momentum is not conserved. And this is kind of a stochastic dynamics that you could write. And again, this problem is also microscopically non-integrable. So this is also quite emphasized by these 3 people in this paper in 2020, that this problem also you could formulate in the form of similar spin chain problem by a suitable reformulation in terms of the right variables. And you could write down its corresponding Markov generator, again in a form which resembles that of the spin chain. But now the algebra that is satisfied by the spins is slightly different by this simple minus sign, and this is known as SU11 group, and this is, again, a non-integrable microscopic dynamics. However, if you do the coarse graining of this problem, again, you get a hydrodynamics, which is very similar looking as that of the symmetric exclusion process. So you'd find the only difference compared to the symmetric exclusion comes is in this part, which is sigma, which in this case is just 2 rho square. Okay? That's the only difference that comes, and of course also the additional terms that you get from the boundary, that also has a different form. Okay? But the point is that this Euler-Lagrange equation also could be solved, and it has the same integrability structure, and you can do the very similar exact solution, the way that we did, the kind of transformation that we did, that kind of transformation also solves it. So these are the 2 examples that I gave you. How about even more general class of system? So even in more general class of system, usually it was difficult to solve this Euler-Lagrange equation. That's where the major difficulty comes in the macroscopic fluctuation theory. But I'm going to tell you that for a large class of systems, we have found a mapping which also solves those Euler-Lagrange kind of equations. So I'll just illustrate this. So the idea is that if you're looking at the hydrodynamic description of these kind of diffusive interacting particle systems with single conserved charge, in that case, your action would look like this, where this is the momentum field, this is the coordinate field, like so rho q dot and minus Hamiltonian. So for the simplicity of presentation, I'm only now going to focus in the strong coupling limit case, so that I don't worry about the boundary terms. And the Hamiltonian now have these two additional paths, where this sigma, which is usually known as the mobility, and this is the diffusivity. Okay? Most of the information about the microscopic dynamics are now at the hydrodynamic scale are embedded in these two transport coefficients, or the functions. Okay? Now, if you can now ask, let's say, the question of large deviation of density, you will do this very similar machinery, and you would get the Euler-Lagrange equation, which would now involve all these d and sigmas. Okay? And in general, it's very hard to solve. But for this very specific problem with this very specific temporal boundary condition, if you use this particular transformation, okay, and it has a motivation why we do this transformation, then so that you make a change of this change of variable from rho hat field to a new field f, then those Euler-Lagrange equations could again be solved exactly. So here I give you a list of those problems where you can solve explicitly and get an exact result for this density large deviation function. So these are a couple of things I already mentioned. This is the symmetric exclusion process, the zero range process, this is random average process, this is a Ginzburg-Landau kind of process. So in all these cases, you can solve the Euler-Lagrange equation. Just to give you what really goes into it, so the Euler-Lagrange equation looks something like this. And roughly what you need to do, once you make the transformation, you have, in terms of new F field, the equation looks like this. And then you recognize the solution, the way it emerges, in the second equation, all these different color terms individually vanishes, so that both equations are satisfied. And then what happens that you have to solve for the F field self-contained way. And in terms of the F field, you can write down the solution of rho in terms of the solution of the F field. So that's just roughly the picture. Okay, so once you solve this, you just put it in the minimal action and you get the rest of it. Okay, that actually brings me to the end of my talk. So I try to give you a sense of how these exact solutions work, how to derive those exact results for integrable systems, and how you can get those results from a more hydrodynamic kind of point of view. But as a take-home message, I find there's two messages which personally I find it interesting. So one is this question of robustness. Okay? So I started with the question that when people try to motivate the large deviation function as the analog of free energy, whether that is really characterizing some bulk property of the system. And this exercises that I presented, at least in certain class of models, shows that fluctuations, even at the non-equilibrium stationary state, has a range of robustness, so that you can think of it as like a state or bulk property of the system. Okay? The second is also I find interesting is that you can have many microscopic models. Some of them could be integrable, so you can solve, and some of them could be better non-integrable, so you don't hope to get a solution. But if you already somehow manage to go to the hydrodynamic level, then the hydrodynamic level, even those non-integrable models could be integrable, so that you can really able to get a solution. So these are the two messages that personally I find interesting from this work. So with that, I thank you for your attention.
Questions? I have related questions. Two questions are maybe related. First, so two related questions. First, you expressed some preference for this MSR action to continue to derive the hydrodynamics. I was wondering whether you could say a little bit more why you want to do it that way, because there are other ways to set up actions. And secondly, I was wondering whether the bottleneck in that approach is not to go from the microscopic action to the macroscopic action.
That is the most non-trivial part, often, and only in the certain case of problems where you can really manage to do the averages over some local equilibrium measure.
So, but in the previous slides or some slide, 3 slides before, you were writing a general expression of this Lagrangian. So for what kind of systems is that then?
Okay. So there is no exact derivation thing. So there comes more of a physical reasoning. And the idea goes back, maybe this is one way to say this. So the idea is that you motivate this kind of fluctuating hydrodynamic equation, saying that there is a conserved charge. So there is a continuity equation, then say there is a diffusive terms, and there's a noise term, and you choose it that the fluctuation dissipation relation happens.
That's already an input, right?
Sorry?
That's
That is already an input. So once you kind of get motivated by that, okay, so this is roughly what is the fluctuating hydrodynamic equation, then you would be able to calculate them by looking at the current fluctuations. So that if you look at this stochastic differential equation, the corresponding Martin-Cgr-Rose action is that one. To prove it for every system, you need to do it precisely, which are very hard to do for general kind of systems. Yes. Satya had some questions? Ah, he left.
Abhishek?
Mike. You need to give him the mic.
So my question was I mean, after you compute the you can solve the Euler-Lagrange equations and find the action, but can you also compute explicitly correlations or?
So once you get the large deviation function,
yeah.
all equal time correlators are embedded in it. So you just expand it and you get it.
And no, like 2 times.
Multi-time. Yes. So we didn't do it for this, but that we already, at least the 2 time, we already did it in 2016 in a paper, not really through the action. And we managed to do it in the action, but we didn't write it in the paper. There was a simpler way to do it. And we have the 2-time correlation, and you can see that there is this anneal and quench difference you could come. Also, there's connection to the fractional Brownian motion for the 2-time correlation of current, of correlation of densities. All of these are done.
But that was not for the open system, right? That
is for an open system,
for
but if you
system.
then look at the center and do a proper limit, you can also capture the result of the infinite system. Okay. So this is a work with Bernard in 2016. I can send you the article.
And I just had a comment, you said the integral, non-integral doesn't. So this, I guess, is specific to stochastic systems, right?
Yes,
where
yes,
probably
absolutely.
integrability means.
So the other part is fully open, and that's where the all hope is that if there is any part of this kind of analysis could be extended for more non-diffusive systems, is fully open.
Can you pass the microphone?
So there is a transformation you mentioned for these class of systems with connecting rho hat to f.
Yes.
In terms of the integral of d by sigma, could you motivate why that transformation?
So it took us a lot of detour to arrive at this. But the simplest thing is to realize if you look at the equilibrium scenario, the rho A equal to rho B, then that problem you can solve by just invoking the idea of time reversibility. So in the equilibrium, there is a stochastic time reversibility. So you can formulate the same thing about deriving, let's say, the Landau free energy of the density fluctuation within the MFT formulation. You will have this coupled differential equation for any arbitrary dn sigma. And in that case, you realize that if you already know that the dynamic should be time reversible, then this transformation where f becomes just a rho bar, it comes out immediately. Okay? So you can solve the equilibrium problem for any dn sigma by very similar looking transformation, which invokes or makes this time reversibility evident. And that was our clue that, okay, I tried, and even like in 2015 when I taught in this Bangalore summer school, I tried to say this, that okay, if you try to extend it for non-equilibrium, it doesn't work. And then after a lot of trials, and we first solved the symmetric exclusion problem, and we recognized that actually it comes in this form. And then once you realize, you try it for other models, and it works. That's all. Yes.
It looks like that this transformation is, if you take this curly bracket in the Hamiltonian equal to 0, then you get this. Right?
Yes, so that is the equilibrium problem.
Yeah, so why H equal to 0, what is the connection to the optimal path? So it looks like that the optimal path has H equal to 0.
That has something to do with only if you look at this specific problem. So the idea is you start with a fixed point, rho bar. So if it's a fixed point, you will only reach it at that point, the Hamiltonian would be 0. And if you now start any trajectory, the Hamiltonian is conserved under this Euler-Lagrange evolution. So the trajectory would correspond to Hamiltonian being 0. That's just the connection. And Hamiltonian is 0, in fact, also for the out of equilibrium. For the equilibrium, the difference is that the term inside the curly bracket becomes 0. But if you're in the outside equilibrium, the whole Hamiltonian with the outside is 0, and that is gives you the Hamilton-Jacobi equation. Okay? It has something simply to do with this particular problem of density fluctuation, where you start with a fixed point. Okay?
Is there a physical interpretation of the field F?
So this is what also we have been thinking of. So one way is that if you look at the F, and if there's a formula, it's rather simple looking, it involves the derivatives of F, this becomes, so let me write down things here. Here. So if you look at the things here, this term almost looks like the effective field. So you have the set, there was no drift. But now if you want to put a field, the field should come as sigma times this field, let's say capital E. So the F, or not the F, but this entire term acts like some extra field, and these fields are really creating those atypical fluctuations.
So you have to multiply that term.
Yeah. So you have to multiply the whole term. So by
rho.
itself, the F,
Okay.
I mean, I asked Bernard, he's told me an answer, his guess, but I don't remember it now.
Right.
But that, because the F also appears in the calculation of SEP large deviation,
Okay.
with the microscopic calculation, and he had some intuition, but I don't remember the.
Because sometimes you can write down like Schwinger-Dyson equations that
Yes,
give you
yes.
an interpretation
Yes,
of the
sure.
field, but
Yeah.
you have to write down the right one.
So
that are an infinite
even
number.
David Gabrieli, for the KMP model, he wrote a paper asking exactly this question. What
Right.
is the interpretation of it? I just don't remember the final claim, but I can
look
tell you
at
the
it.
paper.
Okay, anybody, one last question? Okay.
Yes,
Yes.
there is a question.
Could this method be used for completely irreversible dynamics?
What do you mean completely?
Like, for example, aggregation, which doesn't have a, which
You
has an
mean
absorbing
in presence
state.
of absorbing state?
Yeah.
Because I haven't thought about it, but I would expect some, with certain boundary conditions, some leakage. So probably you were asking whether you can have the hydrodynamics for non-conserved fields. And yes, for the non-conserved field, you can also derive things. But in presence of absorbing state, I don't know an example, so I don't want to give an answer, but I think it's possible.
Okay, thanks very much to both the speakers this morning. We can go and get coffee. Okay.
Thank you.
Because actually, these transformations, Kieran was looking at some of these problems, right?
True.
Found this very complicated transformation.
So that's what I try to emphasize, that